Thank you, Greg.
You're welcome.
Thank you again. It is my goal to show you how the latest HST surveys, the Hubble Space Telescope surveys, have gotten us to a point where we can measure the internal structure of galaxies out to redshift 3, and that those measurements are so good now, and the sample so large, that we have very precisely defined boundary conditions for any galaxy formation model we might want to come up with. And that holds for quenching models in particular, because we can see the differences between star-forming and quiescent galaxies in great detail now.
Sorry.
And it will also be the goal of Eric's talk, and of Rachel's talk after mine. I have a laser pointer, you know.
Thankfully, it's not infrared.
Thanks. Alright, so the two surveys I'm going to talk about, there's one slide on the data. First of all, CANDLES. It's the largest HST program ever conducted. It's a large imaging survey of 5 different fields, 900 square degrees, from the near UV to the near infrared. I'm focusing on the near infrared part because I'm interested in the rest frame optical structure of galaxies out to redshift 2 and 3. A very much parallel survey is the 3D HST survey, which takes slitless spectroscopy with HST of those CANDLES fields, and that very much improves the redshift, the photometric redshift constraints. They get 5 to 10 times more accurate than from photometry alone. I wouldn't call them spectroscopic redshifts yet. You can use them to do environment easily, for example, but the uncertainty of whether something is redshift 1.5 or 2.5, it fixes that problem. So what's relevant here is a sample of about 40,000 galaxies over the redshift range 0 to 3. What these galaxies have is robustly measured sizes and shapes and Surtzic indices. What I mean by robust is described in the 2012 paper. What we've done there is convergence tests, compare shallower with deeper imaging to see if the sizes and the parameters changed. This came up earlier today too. And we've convinced ourselves that with the mass limits we use here at different redshifts, our size and shape measurements are accurate to within 10%, accurate and precise. We investigated both systematic and random uncertainties. But all these galaxies also have photometric redshifts aided by those Grism spectra, and stellar masses and colors. That's all described in Skeleton 14, where for the first time all 5 fields were combined, put in catalogs, along with these structural parameter measurements. It's a very rich data set. If you're interested in this type of stuff, this is the place to go. Okay, so I have a remote. I'm going to split the galaxy population into 2 kinds of galaxies: quiescent or passive galaxies and star-forming galaxies. Throughout my talk I can't help using those two, the terminology early type and passive. I'm going to mix them up, I hope you don't mind. This is my definition of early type, quiescent. What we see here is, came up earlier today, but it wasn't shown really, UVJ diagram. So rest frame V minus J on the x-axis and U minus V rest frame on the y-axis in 6 redshift bins. If you look, for example, here, if you have a blue star-forming galaxy without any dust, you'll be down here. You'll be just blue in all bands. If you put dust in a galaxy, or you see a dead John, you move along this line. That's a reddening vector. So these are the dusty star-forming galaxies. The only way to end up here is if you have a break in the spectrum. So that's the Balmer 4000 angstrom break. If you prefer a more morphological classification, you can also classify by Surtzic index, and it's pretty much equivalent. None of the results I will show later on will really change if I switch from the UVJ selection criterion to the Surtzic index cut. What I've done here is color code all the points by Surtzic index. So higher than 2.5 is red, and bluer is Surtzic index smaller than 2.5. Is there a question?
Keep on going.
Okay.
Frank had a question, I'm answering it.
Okay, Frank. This will be the topic of Eric's talk, how these morphological properties correspond with star formation activity across redshift. The point here just to show that I can change my criterion and I'll get the same result. Good. So I'm not going to look at Sirczyk indices because I don't want to mix my analysis of the structural parameters with the Sirczyk index, which comes from the same measurement, the fitting of light profiles. Good. I put this in just now because Frank keeps saying quenching is how galaxies move from the blue cloud to the red sequence. Now this is the number density of galaxies in this mass G minus R plane, redshift 0.1. This is from Sloan and Weiss. This is a recent project I've been doing with my student, or former student, Yulian Chang. He just moved last week to Paris. So we use the infrared data from Weiss to derive star formation rates. This is a little interlude here. But inspired by the comments earlier today, if I weigh all these galaxies by their star formation rate, then most stars form at this point in parameter space, in the middle of the green valley. Now, as Kevin showed, if you correct for dust, these star-forming galaxies will move down, and this is at 10.4, which is the tip of the star-forming sequence, and it's exactly where I expect it to be. But this whole notion of moving from the blue cloud to the red sequence, most stars form in between, right? The blue cloud is lower mass galaxies, and this contour shows where half of the stars in the universe form today. It's a little interlude. Moving on. Back to the Candles 3DHT survey. Here's the stellar mass versus effective radius plot, where effective radius is measured along the major axis. The blue points are now the star-forming galaxies, the red points are the quiescent galaxies. This is in the lowest redshift bin, redshift 0 to 0.5. I fit these distributions with power laws, where I have a log normal distribution around those power laws in size. The extent of the black lines shows the extent of the mass range over which I fit these distributions. So in the next panel, I show the distribution at the higher redshift. The dashed lines are repeated from the first panel to give you a reference. And the solid lines, the solid lines show the best fit in these redshift bins. So if you keep the reference from the lowest redshift panel in mind, then you see how the distribution gradually moves down. And if you get to high redshift, the offset is very large for the early type galaxies, and quite large, but not quite large for the late type galaxies, for the star-forming galaxies. So there's a couple of things we see here. Rapid evolution for the early type galaxies, but the slope stays intact. It stays the same as it was at low redshift. The late type galaxies also don't evolve in slope, and the offset also evolves gradually over time. So this figure came up earlier today too. These are some of the most cited papers on size evolution. I just want to point out that in this redshift 1 to 2 sample there's a few dozen galaxies. In this redshift larger than 2 sample there's a handful. This is Sloan. And now we have this at high redshift. So these are Sloan-like samples in size. So we can do a much better comparison, much more quantitative comparison, how things evolve over cosmic time. Okay, so we saw that here's 3 panels summarizing the fitting results I just showed. The evolution of the intercept, so the size evolution of galaxies normalized for 5 times 10 to the 10 solar masses. The late types evolve at a moderate pace, the early types very rapidly. The slope doesn't evolve, it's steep for early type galaxies at all redshift, and shallow for late type galaxies at all redshift. And the scatter doesn't evolve either, and it's slightly smaller than 0.2 TeX. I'm comparing here the observed scatter and the intrinsic scatter. That's after taking measurement errors and misclassifications into account. You can look in my 2014 paper for details. So what are the basic implications for this? This is some food for thought. First, for the late type galaxies, the points I'm going to write down here are for late type galaxies. These galaxy sizes are proportional to halo size at all redshifts. But it is if you measure the halo sizes with respect to the critical density. That's when the halo size evolution goes with the Hubble constant at that redshift to the minus 2/3. Because we see a shallow and constant slope that matches with the abundance matching result we see at all redshifts, namely that the stellar to halo mass ratio is not a constant. If it were a constant, then galaxy sizes would scale with stellar masses as to the power 1/3, just like the halos. They don't, the relation is flatter. And finally, as I mentioned, the scatter is slightly smaller than 0.2 dex, which is smaller than the expected size variation at a fixed mass. Now, whether this is going to be very important or has to do with the way we measure the sizes, the way they're compared to the models, we don't know yet, but it is something to keep in mind. This is the first time we measured the intrinsic scattering sizes at non-zero redshifts. Let me also point out, this also came up earlier today, a little interlude, that I'm over this redshift range here, 3, 2.5 to the present day, that's where most of the galaxies formed. In the previous talk, it's good to keep in mind, here's the cosmic stellar mass density as a function of redshift. If I summarize all those surveys by a single line, and we see that 50% of all galaxies in the present day universe forms in redshift 1 and 90% in redshift 2.5. Yes, this is in fact trivial given all the observations we have now, but I think this is important to point out now and then. The star formation activity was highest here, the star formation rate per unit volume was the highest, absolutely, but most stars formed over this period of time. And this is where we can now sample the structural parameters of galaxies across that entire range. Okay, so what did we learn about the early type galaxies? Well, we see very rapid evolution in size for early type galaxies. But this rapid evolution and the addition of new galaxies through quenching works so that the slope and the scatter are preserved. So that's the rule, that if you make a model that quenches galaxies, you have to conserve that slope and scatter. If your model doesn't do that, then it's not a good model. So, do individual galaxies grow in size? I think so. The reason is that the opposite, you could argue the opposite by saying, well, the quenched galaxies, they're all larger, so you get size evolution on average, just by adding larger galaxies to your population of passive galaxies. Let's see if that's the case. In the following plot, I'm going to show all the number density of red points below this line. This line is fixed at all redshifts, and I'm just going to count the number density of galaxies smaller than that value. And I've chosen this slope because it's parallel to the size-mass relation. You can already see, here there's lots of these compact galaxies. This line is actually at a typical size, and here there's none. So this is what that number density evolution plot looks like. If I use that red line, I get this. As long as you have redshift, you first see the number go up, and then it goes down. If I take a slightly more generous cut for small galaxies, then it looks like this. So at high redshift you see this population increase, just in pace with the general population of quenched galaxies. But then they start disappearing. So these galaxies have to physically disappear, they have to grow in size, or you have to blow them up, but you can't do that. So they have to grow, move to a different part of parameter space, they have to end up near the size-mass relation for present-day galaxies, so they have to grow in size individually. Okay, so yes, I'm going to show this plot all the time. So as Frank told us this morning, we have this very nice correlation between internal structure and star formation rate in the local universe. We've seen it before at high redshift. And what we see now is that this contrast in structure gets more and more pronounced at higher redshift. Right? It doesn't disappear. It's not that all galaxies were more similar in the past and then grew apart. No. The difference between star forming and coalescing galaxies at high redshift is larger than it is today, just in size and in average surface mass density. That's mostly the topic of Eric's talk. But this large contrast between these types of galaxies led to this terminology of nuggets, right? There's blue nuggets, red nuggets, and I think that's unfortunate because that seems to imply that there's nothing to these objects, that if you're lucky you can measure their size, but that's it. I think the term nugget implies that there are no features, and I think that's not true. If you look at the structure of these galaxies, there's actually a lot to learn. So a few years ago we pointed out, based on a sample 14 galaxies, that a lot of them are flat in projection. You'll agree with me that this one and this one and this one, maybe a couple of other ones, are flat galaxies. Now if you assume these are disks, then there must also be an equal number of phase inversions. So just looking at the small sample, we already proposed that a large fraction or even a majority of the coalescing galaxies at these redshifts are in fact have a disk-like structure. Now we did a little, so we obviously need to do better than looking at 14 galaxies. So with PhD student Yuyan Chang, we looked at the axis ratio distribution of a large sample of galaxies in candles. That's shown here. Here we have the projected axis ratio, and here the histogram, which we interpret as a probability distribution of the projected axis ratio for the population. So, just at face value, we see this rather broad distribution of axis ratios. If all galaxies were perfect spheroids, there would be one bin here that goes up to unity, and there's nothing here. Right? So, just the fact that this is a broad distribution immediately tells you that there is a population of galaxies with a large variety in shapes, and that lots of them are flat. So we model this with two components. First, we have a population of triaxial galaxies. You can think of those as the classical spheroids. And then there's a population of, too quick. Then there's a population of oblate objects. Now with this sample size, it's probably not justified to fit two components to this axis ratio distribution, and that's motivated, but that is motivated by what we see in the local universe. If you look in Sloan, this low redshift bin, you cannot reproduce the shape distribution of those galaxies with a single population of either triaxial galaxies with Gaussian distributions of their ellipticity and triaxiality. No, you need two populations to explain this wing of flat galaxies. And what the point here is that you see that the fraction of oblate galaxies has drastically decreased from redshift 2 to 0.
Yes. You say oblate and triaxial, underlying that you must also assume for each of those distributions of axis ratios.
Yes. I guess I went too quickly there. Greg, how much time do I have?
2 minutes left.
Cool.
Thank you.
So, our first try is a single triaxial population, and we have 4 free parameters in that model: ellipticity, triaxiality, and Gaussian scatter on both. And we make mock populations and compare it with the observed axis ratio distribution. If you do it for Sloan, you find that you cannot do it with one such population. And this goes back to the 70s. This is what. So what we added an oblate population, so triaxiality was set at 0. We have 2 extra free parameters, ellipticity and a scatter, plus the ratio between the 2 populations. So what we did here was take the best fitting results for the large population of Sloan and only vary the oblate fraction.
No, sorry. You said that the oblate population goes down. But this is a probability distribution. It could just as well be the triaxial population goes way up.
Right.
Because the shape of those curves are exactly the same.
By number density, that's...
Yes. So to interpret this, we would need to look at the evolution of the number density.
Exactly.
And we have a discussion on that in the paper. And you cannot take this population and add triaxial galaxies to it and reproduce the same shape.
You'll have to explain that to me offline.
Yes, I will. So I'm just now going to, if you're still with me, then let's assume that these oblate galaxies have to go away, right? The small galaxies have to go away, and the oblate galaxies have to go away. And I think it both has to do with merging. I think this is a merger-friendly crowd here. We heard it backed up by previous speakers. So I don't have to convince you probably that the merger origin of the most massive galaxies in the present universe. What I mean by that is, here's again the projected axis ratio, now as a function of galaxy mass. This is for a sample of local early type galaxies, again selected by star formation rate. You see that here the axis ratio distribution is broad, so rather oblate-like. But if you go to a high stellar mass, with 2 times 10 to the 11th, above that mass you only see round galaxies. There's nothing that's flat in projection. So, and this is the plot that Marianne also showed. And I think the implication is very simple and very clear. The only way to grow beyond that ceiling mass for disks is to merge, to accrete galaxies. And I think that this is the same thing as the size evolution, right? You build up the outer envelopes of galaxies. It's the same thing as the disappearance of the disk-like structure of those galaxies, because those mergers will destroy the disks. So that all fits nicely together. I'll leave you with my conclusions, because Greg might get upset.
Angela?
In a question about the last plot that you showed, there is a thing that should be clarified. So when you plot these, you have both the elliptical and S0 inside here. Okay? So we know S0 they have this. Okay? So all the low VA that you have a lower mass is just due to the S0 population. If you take a relatively clean sample of elliptica and you plot the B over A, that becomes flat with a little bit downtone towards the very massive.
I am happy to describe this trend as a changing fraction of elliptical versus S0.
Okay, so but the interesting thing is that when I use instead the B over T, okay, that of only the elliptical galaxy, so where the BA is 0.8 for everything mainly, so then you still see that it dropped down. So there is this component is seen even with all the elliptical galaxies.
The practical difficulty there is that you're first cutting your sample by visual classification into early types and S0s, and axis ratio has to be part of that classification.
Yeah, so
right? So
let's
then,
say, yeah, it's fine that, but if you, let's say, you can also fix the B over A, but then you look at the B over T. So the B over T is more sensitive if you have a disk or not there. Okay.
Right.
And so you see that below 10 to the 11, 2 10 to the 11, really you start seeing the disk component there. Although the B over A is fine. So you can play with also the inclination, all this stuff, but we need that. And you see that really there is this component coming towards that. So the B over A is not really clean, because when you are a disk, you know that you are affected, right? The B over A.
right. But the overarching point is that you're not allowed to have a disk when you're over beyond a certain stellar mass. But
Exactly.
yeah.
So my point is just, that it's better to use the B over T, because the B over A, if you add the S0, it can be really tricky, right? Because S0, we know that they have clearly this.
Yep.
Tim? Could you say a couple of words about how this matches up with the Atlas 3D picture, where even if you just take the morphologically classified ellipticals, 60% of those are actually fast rotators and consistent with being oblate? How that works with the numbers you said for Richard Zero, where you had 90% as triaxial?
Exactly.
You mean?
Yeah.
So your conclusion was you had to get the oblate ones to go away,
Yeah.
but if Atlas 3D is right and 60% of
Right.
ellipticals that look elliptical on the sky are actually oblate, then you
So I don't think there's tension actually, because most of these galaxies are 10 to 11 to a few times 10 to 11 solar masses.
Okay, so they're high in the mass range.
Yep.
Okay.
If you make this path for Sloan in the 10.5 to 10.8, then you get those numbers back.
So
I
it's
would
the
need to
sample
look up
selection.
the exact numbers. That's in another paper. No, it's in the same paper. So this is dominated by the slow rotators. I think this transition here is more or less at the same place above a few times 10 to 11 solar masses. And then we see the slow rotators here and here the fast rotators.
Okay. Is that
Same question.